This is part 2 of the book summary for Chance by Amir Aczel. So chapter 7 is Random Walks and Gambler's Ruin. He starts by explaining this idea of a random walk, like a drunk walking around a lamppost. Sometimes I look out the window and I see that sort of situation. And anyway, he starts off with this graph from Feller, which shows 10,000 tosses of a fair coin, and it shows the cumulative results in terms of how many heads and tails have happened so far. And it's quite a remarkable graph because it really does have some deep troughs and some huge mountains on there. So you can look at parts of this and say, wow, there must have been loads of tails going on for that steep bit going down, and then there's this steep ascent, so there must have been lots of heads going on there. So people say that this is, like many things in probability, quite surprising. We're not very good at understanding randomness intuitively. Only when we have experience of it do we know the classic situations where actually our intuition lets us down. Well, this is just that sort of remarkable result, and I've actually experimented with this in Excel, and it's a different result every time, a bit like a lava lamp, but you can do, say, hundreds of spins quite easily in Excel and get a graph up. So he said it might shock a lot of people, and he also shows an interest in the zero crossings. So this line crosses zero, and Aczel is interested in that. So he next starts discussing the game roulette in the casino. That's the one where the ball spins round and round, and it goes jigga jigga jigga, and it lands in one of the numbers from 1 to 36 or something like that. And there are 2 zeros in American roulette, but 1 0 in European roulette. Anyway, so he says immediately, he says with this, it's not a random walk. This is downward drift. And what he means by that is the more you gamble, the more the house will always win. So it's not 50-50, and whilst it looks like it's almost 50-50, it isn't, and over the long run that has a big consequence. So when it lands on 0, people tend to say the house wins. It's not red, it's not black, it's 0, or it's 00 in American roulette. And that seems subtle, but the consequence is that there is now downward drift. He also says, if that wasn't bad enough, and even if it was fair, with no zeros, even if it was with no zeros, there's a gambler's ruin theorem, which says that playing against a much wealthier adversary, the gambler will lose, probability to a probability of 1. And he says that the Feller chart explains why this is to some extent, but he doesn't actually explain the full theory of gambler's ruin. Next he says that he describes 0 as an absorbing state of the random walk. But then he goes on to say a bit more about downward drift, and he uses an example from some other authors called Dubins and Savage. And the idea here is, what if, say, the mafia forced you to gamble, and they said you had £20,000 and you had to try and win £40,000 in 24 hours, and they sent you into the casino, and you knew that you were going to get shot or something by the mafia if you didn't do it. It's maybe a slightly silly example, but the idea is, what if you actually really had to gamble? How could you do it? And the distinction really is between bold play and cautious play. And what they say here is that bold play is actually better in terms of trying to if you're trying to go from 20,000 to 40,000, it's going to be very difficult to do it, but you're better off with bold play than cautious play. So something like all on black with an 18 out of 38 chance of winning would be bold play. But cautious play can really fail very badly because of downward drift. So if you're the more bets you do because of downward drift, it becomes terrible in terms of winning money. So further than this, he's actually got this formula for showing just how bad cautious play can be. Difficult to explain it, but so the probability equals, and then the numerator is 1 minus open brackets q over p close brackets to the power of m, and that's divided by, and so on the denominator you've got 1 minus open brackets q over p close brackets, and that's to the power of m plus n, where m is your starting fortune and m plus n is the fortune you're aiming for, and p is your probability of winning a single bet and q is your probability of losing a single bet. It's not really a formula which people need to remember, but it's a bit of a curiosity. His example is, well, what if you had 20,000, so 20k would be you're aiming for m plus n, which is 40k in this example if the mafia forced you to gamble. So small p is 18 here and q is 20. You put it all through that formula and you get 0.11. So your chances of doing it with cautious play are awful. 11%. So this is a sort of mathematical proof of how, if you actually were forced to gamble to try and win big, bold play is optimal and cautious play turns out to be terrible. Next he goes on to explain doubling systems, which are sometimes called the martingale, and he's quite critical of it and explains the danger that while some people think they're going to always win, the danger is you get in this situation where you're putting down huge sums of money to try and win $1, because that's what you tried to do 6 rounds ago or something like that. So he's critical of that system. He then goes on to explain his favourite variation, where he just accepts losses after doubling it a couple of times, which is much better than what some people do with the doubling system. But still, I think it's a bit controversial, so I'm not going to really mention that or analyse it too much. But he describes quite a nice situation where he's with his wife and they go to this casino, place one bet, and then go to dinner. So it's quite a nice example. Anyway, at the end of the chapter, he mentions Brownian motion, which we all know in science. It's sort of like that random movement of the gas particle or the smoke particle, and he says that's very much like the random walk. So Brownian motion is how he ends the chapter. Chapter 8, what is randomness? So Aczel introduces the runs test for randomness, which is something in statistics books, which relabels digits as odd or even, and then can give a sort of a rating of how likely that sequence is to be random. It's called the runs test for randomness. Next, he goes on to describe. He shows an interest in these sorts of situations which are also almost random but not random. And one of his good examples was seats filled at a bar. So sometimes, if you look at a bar, it'll be, there's someone sitting there, then an empty seat, sitting there, empty seat, sitting there, empty seat, sitting there, empty seat. Obviously, they've got choice and they're not sitting right next to each other. So that's not random because there's human choice involved. But sometimes it might appear to be random. So he's interested in these situations which might seem random but are not. And he makes a key point about true randomness actually has these aggregations which we don't expect. Unless you're really familiar with randomness. So if you ask school children to try and write a random sequence of coin flips, what they should do is to write, to have some strings where it's like 5 heads in a row, because it will happen. But they don't, because they think that 5 in a row doesn't look random. So we're actually basically wrong about what we think random is a lot of the time. And so these aggregations are where you get these clusters of strings of results. Okay, chapter 9, Pascal's triangle. This is a wonderful thing in mathematics, which I'm sure we've all come across. It's that triangle with the ones, and it starts 1, and then it goes 1, 1, and then it goes 1, 2, 1, and then it goes 1, 3, 3, 1, and then it's 1, 4, 6, 4, 1, and 1, 5, 10, 10, 5, 1, and you keep adding the ones above to get the ones below. So 17th century, Blaise Pascal and Chevalier. So it has applications in pure maths dealing with prime numbers. It provides coefficients for the binomial distribution, and it also provides expected results for coin flipping. So if you have 3 flips of a coin, the probability of results are 1, 3, 3, 1 for the various combinations. And if it's 4 flips or if it's 5 flips, it's the applicable line in Pascal's triangle. One of the interesting points which Aczel makes is the key observation that as the number of flips increases, the probability of exactly half heads and exactly half tails decreases. So if you're flipping the coin 4 times, there's a 6 out of 16 chance of this, dead even heads and tails results. But if you flip the coin 6 times, it's 20 out of 64. So the probability of exactly half heads and half tails decreases as the number of flips increases. And that's really interesting. You might also notice that the Pascal's triangle looks quite similar to the normal curve, which is something which he covers in a later chapter. Chapter 10 is the inspection paradox. This was a brilliant chapter, actually. So he starts off saying all of these examples, like you look at a light bulb and it claims 2,000 hours on the box, but if it's 8 hours per day, 2,000 divided by 8 equals 250 days. Well, you've used your light bulb a lot more than 250 days, so what's going on? There are other examples of this. Basically, he says it's sort of like an infant mortality argument. Some of the light bulbs will blow at a very young age, and that pulls the average down. So quite often we're in these situations when what we're actually doing is inspecting a survivor, and there are some cases of infant mortality. So once you're inspecting a survivor, actually the probability of it being above the average is very likely. And I think Alan Turing used a similar example of if you're considering a man who's 52 years old, well, the chances of him living to at least 70 are much more, because he survived until 52, and there were all these cases of infant mortality sort of argument, which has brought the average down. So other examples of this are the battery life in a flashlight, in a torch, and he also talks about bus times, which is a bit more complicated actually, I thought, but the bus times are meant to be every 10 minutes, so why do we always think we're waiting more than that? Well, he says that because it's very difficult for the buses to arrive exactly 10 minutes, so sometimes there are gaps, and sometimes they're close together as well. Now, because of that, if you sort of drew it out with sort of like planting trees, you'd have some close together and there'd be some gaps. Now, because you've got that situation, he says you're more likely to arrive in the middle of a big gap, and that's why the bus times are not 10 minutes. Okay, so chapter 11 is the birthday problem. This is a classic in probability theory. So you've got lots of people in the room. What's the probability that two of them will share a birthday? And initially you might think, wow, that's really unlikely. And actually it's one of those things which is mathematically very likely if you've got enough people in the room. So you've probably come across it before. The way to do it is actually a bit like one of the earlier chapters. You use the complement for this. So you do 1 minus, open brackets, 364 out of 365, that's the second person, times 363 out of 365, that's the third person, times 362 out of 365, and so on for the number of people that you've got. And then you close the bracket and you hit equals on the calculator and you get the result. So actually, if 23 people are in the room, the probability is 0.5073. So it's actually over 50% likely, with just 23 people in the room, that two of them are going to share a birthday. What's great about this chapter is he goes on and explains something which is a bit more advanced, which some people don't know about the birthday problem. There's a sort of balls and buckets formula for this, which you can do. And it's if you want even odds with this type of problem, then you do 1.2 times the square root of the number of categories. And a similar variation on that, if you want to find out 95% probability of the balls in the bucket situation, then you do 1.6 times the square root of the number of categories. So if we apply this to the birthday problem, then we can do 1.2 times the square root of 365 days in a year, and we get 22.9 people. So that's why if you have 23 people in the room, it's just better than half even odds. Now, if you do 1.6 times the square root of 365, you get 31 people. So if you had 31 people in the room, there's actually 95% probability that two of them are going to share a birthday. It's really likely, 95% probability, and that's actually just with 31 people. So it shows how counterintuitive the results are. Next he uses an even more far-out example. What about same birthday and same profession? Well, for that he says 365 days a year, and he imagines a world where there are only 28 professions, and he says that's about 10,000. So if we then put that into our formula, 1.6 times the square root of 10,000, it's actually 160. So only 160 people for a 95% probability of a match. So Aczel sees all this as another example of unexpected aggregation. But he also explains as a final point that it works because it's not specific to any particular person. So if you said, what's the probability of one of the 22 people in the room matching my own birthday? Well, because you said my own birthday, that is actually quite unlikely. So you can do 1 minus brackets 364 over 365 and take the bracket to the power of 22. It comes out as 0.06, so only 6% likely. Finally, we're just going to wind this up. So chapter 12, coincidences. He talks about the 6 degrees of separation, which you might have come across before. The idea is that we know everyone else on the planet by 6 degrees of separation. So I don't know, you once shook hands with I don't know, John Major or someone important, and John Major knows all these other people. It's possible that we all are connected by 6 degrees of separation. Incredibly difficult to prove it. I mean, it might be 7 or more, but it's quite a compelling idea, and some people apparently are very good connectors, and know lots and lots of people. Chapter 13 is a succeed in love equation. I think he was having a bit of fun with this chapter. He said, when should you settle down in dating? And he said he's used this example of 1 over e, which is a special number in mathematics. And 1 over e is 0.37. So what he says is you should estimate the total number of people you think you could date in your life, and after you've been through 37% of them, you should then start looking for the one that you're going to marry. And that was his example. And he said, wouldn't it be funny if your parents gave you that advice? And that's the end of chapter 13.